Okay, cool, perfect. Thank you. So thank you very much. Good morning or good evening, everybody. Today I'd like to show how we can constrain the multi-phase structure and the physical conditions of the ISM, and in particular the low metallicity ISM using far infrared lines. And first, I want to ask the question of why do we want to do that? Why should I care about the multi-phase structure of the ISM if I'm interested in galaxy evolution or planet formation? Well, the reason is that because all scales in the universe are connected. Galaxies form from accreting gas over large scales, several tens of kiloparsecs. And within these galaxies, you need to zoom out many orders of magnitude to find one region, one star-forming region, which the condition of these star-forming regions are set by the dynamics and the morphology of the galaxies. And in turn, the properties of these giant molecular clouds are going to set the initial conditions for star formation happening in the dense core. So again, orders of magnitude smaller in size. And within these cores, you can again zoom several orders of magnitude to find one star formation, a single star forming with its protoplanetary disks. And it's difficult to cut this entire range of sizes because all of these scales are connected through feedback, so energy and momentum being re-injected from the small scales to the larger scales. So it's 12 orders of magnitude here that you need to cover to understand really star formation and how star formation and galaxy evolutions are linked. And it's not only spatial, but also each of these steps covers a different time scale. So there is 9 orders of magnitude here between a supernova explosion and galaxy evolution taking place over several gigayears. So if you want to accurately understand how star formation happens and how galaxy evolves, you need to take into account what happens on the small scales and on the larger scales. Computationally, it's of course impossible to model this from first principles. So you require models and simulations require sub-resolution prescriptions. So to basically cut this range of scales at a certain point. And the main problem is that these physics of star formation and feedback are unconstrained observationally. But they're going to make a huge difference in the resulting simulated galaxies. And this is visible here with these 3 snapshots here of a simulation with identical initial conditions. But the only thing that is different is the criteria of which gas is forming stars. Is it only the self-gravitating gas on the top, or the gas above a certain density threshold, or only the molecular gas on the bottom plot? And you see that all 3 models are plausible physically, but we don't know which one happens in the real universe, and therefore we don't know which or if any of these 3 simulations actually describe correctly the observed process of star formation and galaxy evolution. And this is the same problem with feedback. You can model feedback through supernovae or photoionization or combination of both. And again, these things make sense. But choosing one or the other is going to lead to completely different galaxies simulated, as you can see, again, 3 snapshots with identical initial conditions. So to make galaxy simulation predictive and connect to the observed galaxy population, what we need is an accurate description for the cloud scale physics of star formation and feedback. And the way I want to approach this question today is by trying and answer part of it, which is what is the reservoir of the star-forming gas, and what is the effect of feedback on the surrounding medium or around star-forming regions. So to do that, we need to start by understanding the multi-phase structure and the physical conditions of the ISM. And this we can do using infrared observations, but using many of these line emissions, so multi-wavelength observations to probe these multi-phase structures. And to try and get which lines can be interesting to look at, you can look at this plot showing the critical density of different emission lines on the y-axis as a function of the energy to create the ion that are going to emit these lines. And this plot can be roughly divided into two parts: a neutral gas emission from the neutral gas on the left, and emission from the ionized gas on the right, where the distinction is whether hydrogen is ionized or not, so above or below 13.6 electron volt. So with SOFIA and FIFI-LS instrument, we have observed in several galaxies several of these lines, so mostly the brightest ones. And you can see that we have information both on the neutral gas and the ionized gas at different energies and at different critical densities. And we'll use that later to be able to measure this the density of the gas and the hardness of the radiation field. Now, to better understand the multi-phase structure of the gas, it's interesting to look at it in a variety of environments. And the axis I would like to look at is metallicity. And I don't have to make a mystery of it because you've shown that picture already. So you know that the structure of the ISM is very different between solar metallicity and low metallicity environment. And in particular, at solar metallicity, so H2 and CO trace very well each other. And there is only a little, a small envelope of H2 in the neutral gas around the CO core. When you go to lower metallicity, the picture changes radically. There is less dust, UV photons can penetrate deeper into the cloud and dissociate CO, while H2 is going to be efficiently self-shielded and can exist in this CO-free envelope here, which can represent a significant reservoir of molecular gas that is unseen if you use CO to trace it. So we'll try to look, I've tried to look at low metallicity galaxies to investigate what is the reservoir, the total reservoir of molecular gas for star formation. And finally, it's interesting to do that, of course, at high spatial resolution to be able to resolve potentially star forming regions, or at least try and resolve galaxies. So here are the 5 galaxies that I'm going to look at, so at different distances. So in the LMC, we zoom in into one single star forming region, 30 Doradus. We also have looked at IC10, so several star forming regions here. And then we have 3 galaxies that are a little bit further away, so that we can look at in a more integrated way. So NGC 1140, NGC 1569, and NGC 5253. Okay, so using these galaxies and these multi-wavelength observations, these are the goals that we want to achieve. And this is the goals and the summary at the as well, because I'll show this slide at the end. So I hope I can cover all of this. But basically, the goal is to use a combination of multiple far-infrared emission lines to reveal the physical properties of the ionized, neutral, and molecular gas. So with that, we'll be able to measure the electron density, the hardness of the radiation field, porosity, the 3D structure, the total mass of the molecular gas. And the goal is to be able to assess the effect of feedback on the small and the large scales, and quantify the potential reservoir of molecular gas for future star formation. So I want to start by flashing very quickly the data that we have. So the line fluxes have been extracted from the cubes using a similar technique as what Jessica just explained. So for 30 Doradus, we have lines from the ionized gas and from the neutral gas. Same thing for IC10, so by combining Spitzer, Herschel, and SOFIA data. So many of these lines are from the ionized gas. We also have C2. And for these 3 galaxies that are a little bit further away, we have both all 3 lines from PAX and from FIFI-LS. So what can we do with all of these observations? The first thing is that we use these lines as an empirical diagnostics to measure the electron density in the ionized gas. And for that, we can use ratios of lines that are at the same energy, so same ion, but different critical density, the ratio of the O3 lines and the ratio of the S3 lines. The reason for that, so the O3 line ratios, the O3 line ratio is a valuable diagnostics that we can now get with SOFIA because we have access to the 52 micron line. And what you see here is that, so analytically, we can predict what's the variation of this ratio as a function of the electron density in the ionized gas using the theoretical collisional rates. Now, if we overplot the ratio that we have inserted around us, so between sort of 0.5 and 2, we get then electron density in the ionized gas that is below 600 electron per cubic centimeters. We can compare that with what we get in IC10, so it's a little bit higher, as you see. So between 350 and 1800 electron per cubic centimeters. And we can also do that for the other galaxies that we have. And by combining our observations of this ratio with the theoretical prediction, we can get a map of the electron density and how it varies within the galaxy. So in particular, if we look at IC10, we see that different regions, different star-forming regions within the galaxy have, as indicated by these different color points here, have different densities as measured with the O3 line ratio. But what is also very interesting to look at is how this compares with the electron density measured with the S3 line ratio. And you see that we get completely different results here, where the S3 probes densities are much lower than the O3 line ratio. So O3 and S3 trace really two different components of the ionized gas. And we can go even a bit further and compare, so what is this derived density as a function of the ionization potential? The ionization potential of O3 is higher than the one of S3, and we can also add another point here, which is the ratio of the S2 lines in the optical, with, again, lower ionization potential. And what you see is that the highest densities are traced by the lines with the highest ionization potential, showing that the denser clouds are closer to the ionization source. So that's a first diagnostic by taking basically vertically lines on a vertical axis here in this plot. But we can also look at it more horizontal axis here and probe the hardness of the radiation field by using the ratio C2 over O3. And we've known already for quite some years that the ratio O3 over C2 is much higher in dwarf galaxies, so at low metallicities, these are the color points here, compared to more solar metallicity galaxies. And this is true in an integrated way, so each point here is a galaxy. This is also true if you zoom in on a single region here, where you see that this ratio, so here, sorry, it's C2 over O3, but so the other way around, but this ratio is low, hundreds of parsecs away from the ionization sources, which is this cluster here delimited by this yellow circle. So this means that at a lower metallicity, the ISM is more porous. UV photons can escape by traveling over hundreds of parsecs through low density channels. And you can also probe this by measuring the H2 escape fraction from dwarf galaxies, and you find that it's higher at low metallicity than in higher metallicity environment. And just a very quick snapshot here of a very recent ALMA map of CO inserted Aratus, and you can see, so the resolution of ALMA here is 0.4 parsec, and you can see this very small CO clumps here. So you can actually see how porous the medium is. And these CO clumps are based in a neutral and ionized medium. Now let's move on. So we've seen a couple of diagnostics for the conditions of the ionized gas. Now let's continue to the neutral gas or the photodissociation regions. So photodissociation regions, or PDRs, are regions where the heating and the chemistry are dominated by UV radiation. And so this is a schematic, so showing that what we call the photodissociation region is basically start at the transition where H plus, with the medium H plus dominated becomes H, so neutral hydrogen dominated. And the diagnostic that we can use to probe this medium are basically these lines, so C2, O1, C1, and CO. But there is a little caveat here, is that as you've seen maybe in one of my first slides, so showing that plot here, the separation between the neutral gas and the ionized gas, is that C2 is not in blue or is not in red, but I've circled it in purple. And the reason for that is C2 can actually be found both in the neutral gas and in the ionized gas. So before using it, using Cu2 line as a diagnostic for the neutral gas or the PDRs, we need to make sure what is the fraction of C2 that is emitted from the ionized gas or the neutral gas. So for that, we need to take several steps. The first step is to estimate the electron density. So for that, and the electron density in the low in the gas at low ionization. So we can use for that the ratio N2 122 micron over N2 205. So I'm showing here for the example of Certito Radus. So the measure range of the N2 ratio is here. And by comparing it with the predicted, the analytical ratio, we get a density between 10 and 100 electron per cubic centimeters. Okay. Then if we take this density, we can estimate the C2 over N2 ratio analytically predicted in the ionized gas. And between 10 and 100 electron per cubic centimeter, this is the predicted ratio in the ionized gas, between 0.5 and 1.5. But now if we compare this prediction to what is actually measured in Certito Radus, we see that there is an excess of C2. The ratio that we measure is much higher than what is predicted, which means that this excess of C2 comes from the neutral gas instead of the ionized gas. If you do the math, you can estimate that between 92 and 99% of the C2 lines is emitted from the PDRs. So it is a good diagnostics, especially in this region here, but also in general, a large fraction of C2 actually comes from the neutral gas. And in Certito Radus, we can use it as a probe of the neutral gas and the PDRs. So now how do we, how can we actually probe the conditions of the neutral gas? So for that, we have used photodissociation region models, and the way they work, so this is a schematic for 1D, so one-dimensional PDR model. So typically they assume ionizing source, so with a radiation field that I call GUV here. And so you have this 1D cloud here, so 1D slab of gas, which can also be illuminated from the other side or not, it depends. This slab of gas has a certain size, so AV, the total AV. And in the model that I've used, we've chosen to have an isobaric model, so with a constant pressure throughout this slab of gas. Other models can assume a constant density, so just a matter of what equation of states you choose. How a PDR model works is that at each position along the cloud, the PDR model will solve for the chemical balance, the radiative transfer, and the thermal balance. And each of these three processes influence each other, so it's an iterative process at each position along the cloud. So you do that for for a grid of GUV, for a grid of pressure, and for a grid of total sizes, and predict what is for each of these parameters, what are the emission lines that are coming out of this cloud. So we can compare these predictions with observations to try and constrain these parameters. And this plot here is showing the combination of GUV, so incident radiation field, and pressure that are necessary to reproduce the observed ratios inserted radius. So O1 plus C2 over far infrared in dark blue, and O1 145 over C2 in red, and O1 63 over C2 in blue in cyan. The first thing that you can notice here is that there is no one single solution, one unique solution that will be able to reproduce all of our observations. First, the red line and the cyan line never cross, so it's impossible to both reproduce 0163 micron and 145 micron at the same time. And one reason for that is that the O1 line can be self-absorbed. So if there is cold gas along the line of sight, the actual observations will be lower than what the model would have predicted. So for that reason, we choose to exclude this line for the moment and just look at the red one and the blue line and the dark blue. Again, there is no one single unique solution that gives us the answer for what radiation field and what pressure exists in this region. Because there is a degeneracy here. So one way of being able to break this degeneracy is by a continuity. So this is one pixel inserted radius. If you look at many other pixels, you don't want this solution to jump between the two. That can give a hint of what the most plausible solution is. The other one is to compare this incident radiation field to what we can measure as the emitted radiation field. So if you know how many stars are emitted UV, if you know the type of these stars, then you can also determine which of these two solutions is the most likely one. In the case of 32 radius, so the high GUV and low pressure solution was the most physically plausible solution. Well, the example I'm showing here is based with using the Meudon PDR code, but many other PDR codes are available. This is a non-exhaustive list. I encourage you, if you're working on this or if you're interested in this, to see the paper by Röhlig et al. 2007 and this website here that has been recently made available, showing a comparison between the predictions of different PDR models. Okay, so using this line, so O1, C2, far infrared, we can determine GUV and the pressure. Now there is a third parameter that I've talked about, which is the total size of the cloud. And for this, we need to compare lines that are coming from different depths into the cloud. So C plus and CO, or C plus and C1. In 32 radius, again, if we compare the predicted line ratio with the observed line ratio, both for C2 over CO and C2 over C1, this is what we get for different total clouds. So the most likely size of the clouds in 32 radius are between 1.5 and 3 magnitude typically. So we can do that for using CO2, C1, O1, and the far infrared for every pixel of in the 32 radius map, and constrain a map of the pressure, the incident radiation field, and the total size of the clouds. And what I find interesting here is to highlight the fact that the peak of the incident radiation field is not where the emission is, which is the cluster here with this red circle, but it's in the incident radiation field. So it's really where the matter, most of the matter is. You can do this for, so this has been done in the Milky Way, in the Large Magellanic Cloud, and in integrated galaxies. And it's interesting to see that there is a correlation between the thermal pressure and the incident radiation field that can be identified over several orders of magnitude. Despite the wide range of methods and the wide range of sources, which are all of different types, these observations follow a similar trend. So that's very interesting. And this black line here shows the balance between H2 region pressure and PDR thermal pressure at the Strongen radius. And the gray line here shows the prediction if there is an equipartition between thermal pressure, turbulent pressure, and magnetic pressure. So there is a qualitative agreement here, but you can see that mostly full galaxies are lower than this line, and maybe this is caused by averaging a significant reservoir of diffuse gas. Now, very quickly, I said that you could compare the incident radiation field with the emitted radiation field, and this can also allow you to measure the physical distance between the stars and the cloud. Basically, the difference between these two is going to be the ratio between the projected and the physical distance, and that allows you to reconstruct the 3D structure of the gas around the cluster. And this is the modelization of the PDRs around inserted Doradus. But I'd like to finish now with the estimation of the total reservoir of molecular gas. So now that we have constrained all the parameters of all the properties of the gas, we can, from the model, know exactly what the abundance profile look like for different elements within the cloud. And in particular, we can look at where the gas is CO dark. So where we have a lot of H2, but where the abundance of CO is still quite low. And we can measure how much mass there is here from the model. So that's what we've done in Doradus. And what is interesting to do now is to compare this predicted total mass with what would be estimated by the CO emission, just multiplied by the typical XCO factor. And what we've shown is that more than 75% of the molecular gas is actually not traced by CO in this region. So to summarize, I've shown that we can use a combination of far infrared emission line to reveal the properties of the gas. I'm not going to go through it again, but the goal is to estimate, from this, estimate the effect of the feedback on the large and small scales and calculate the potential reservoir for star formation. In a more, maybe a more scientific point is that we've identified that there is a large reservoir of CO dark gas in massive star forming region, which is driven by an intense radiation field and a high porosity of the gas, which allows a large fraction of the photons to escape. The next step will be to bridge this cloud scale condition to a larger galactic or larger scale environment. And finally, just a couple maybe word of advice: go to a telescope, go observe with SOFIA especially. And what I encourage you all to do is, if you have the opportunity to go to an observatory or work with the expert of an instrument, it's interesting to do not only at the data reduction, but also at the proposal stage, to know what the instrument can do or cannot do. And finally, just don't focus on one topic, but learn around the subject, multi-wavelengths, multi-scales. I think this is the key to solve your problem. So thank you for your attention, and I'm happy to take questions.